Now it's time for the more substantial lesson for today, and that is going to be section 4.2. And we're going to look at some chemical reactions and the equations that we would need to write, and then that is going to help us transition into these net ionic equations, which you may not be too familiar with yet. So let's get there. So remember, a chemical reaction is going to involve the changing of molecules or atoms, from one substance to another. So we are going to use equations to show our chemical processes that are happening. But not only that, but we could also use that to show a physical process, such as a change in state. So in a chemical change or a chemical reaction, we're going to see that the atoms are being rearranged. So perhaps atoms are coming together to form a molecule by forming a bond. Perhaps a molecule is breaking apart into either smaller molecules or the atoms themselves, or some other, perhaps a change in combination by the breaking and then the formation of bonds. So you have a whole bunch of things that are happening within a chemical reaction. It does not necessarily have to be one or the other. It could be both. So the most important thing here for a chemical reaction is that we are not creating anything, and we are also not destroying anything. So the conservation of mass is super, super important, and making sure that we have balanced both sides is super important. We need to have the same number of atoms on one side as we do on the other. So on the left side of the arrow, we're going to have our reactants. On the right side, we're going to have the products. Super basic stuff, sure, at this point, but keep in mind that we need to have the same number of atoms as reactants as we do as products. Things are not going to become created nor destroyed within our chemical reaction. We do not have that ability. That does not happen in nature. We don't have the ability to just pull helium out of a hat or something like that. So don't get any crazy ideas. In a chemical reaction, our molecules or our atoms, in undergoing a chemical reaction, bonds are going to be broken or formed, perhaps both. And just keep in mind, once again, that you have the same number of reactant atoms as you do product atoms. So let's get right into an example here and the combustion of methane. So anytime we have something that is combusting, okay, the process of combustion involves the addition of oxygen. So essentially something is going to burn, and that would be our fuel. So in this case, the methane is our fuel, and it's going to react with oxygen at a very high temperature, and in doing so, it is going to release heat. So we need to balance this equation. So we have CH4 plus O2, and that yields CO2 and H2O. So let's take a look and see if it is balanced. So on this side, how many atoms of each thing do we have? We have 1 carbon, 4 hydrogen, 2 oxygen. Over here, we have 1 carbon, 2 oxygens, 2 hydrogens, and another oxygen. Okay, so nice thing, carbon is certainly balanced. There's only 1 on each side. We do have 4 hydrogens over here, and then only 2 over here. So what we would need to do is even that out. So we would add a 2 here to indicate that we have 2 H2Os, which would mean that we would have 4 hydrogens now. And that's going to mean that the hydrogens, we have the same on both sides. So then we would need to make sure that our oxygen is balanced. So we have 2 over here, and then we have 2 there. And then if we have that 2, we would also have 2 oxygens here. So that would give us 4 on this side and then 2 on this side. So we could balance it by adding a 2 here. So we would have the same number of carbons because we did not change methane or the carbon dioxide, but we did add a 2 here and we did add a 2 there. So those numbers that we added at the beginning of these molecules are coefficients. So the coefficient numbers just indicate how many of the substance, whatever that may be, a molecule or an atom, it just indicates how many we have in our reaction. So we'd have 2 oxygens and 2 waters, and in having 2 of each of those, that helps to balance the number of atoms that we have on both sides. So do we need to use a 1 as a coefficient? No, we do not, okay? But anytime there is 2 or more, we do need to use a coefficient. And that coefficient is just the number at in front of the molecule or the atom. Okay, so there we go. Now we got it all down there on our slide. But we're not finished, and I will bug you guys throughout this year. You need to also indicate the physical states. So we need to indicate if it's solid, liquid, gas, or aqueous. And well, all these things are going to be gases. So we need to add a G in parentheses at the end of each of these things. There we go. Now it looks a lot better. So we have our coefficients, which means that the number of atoms on both sides are balanced. And we've also included the physical states as well. All these things are gases. So here is another example. And this is something that I would like you to do on your own. And then later today, I will provide an additional video where I actually go over balancing this as well as some of these other examples. So we are going to combust liquid ethanol. So C2H5OH, that's what we have here. We have to figure out what it is going to react with, but we know that this is a combustion reaction. So that probably means that it is going to combust with oxygen, don't you think? And if we have oxygen here and then we have all this carbon and hydrogen here, well, guess what? That means that we're going to end up with carbon dioxide and water. Okay, so those are some clues here to help you out. So the ethanol is going to react with oxygen, and then it's going to release heat in forming carbon dioxide and water. So there you go. Now it's going to be up to you to balance it by adding coefficients. But not only that, but also I would like you to include the states for each of these things using what we knew from the previous reaction with methane, but also the information that is provided in that first sentence. Okay, so go ahead and pause the video now and then do that, and then we will move on. And I think that's enough time, so let's move on. So just a few tips for balancing equations at this point. So first is just the basics, figuring out what exactly is happening, what are the reactants, what are the products, what are their physical states. That's going to help us get the species down on paper, and then we can balance them. Okay, by adding the coefficients. And what you'll want to do is get a count of the number of atoms on both sides. And if they're the same, then you don't need to do anything. But if they are not, then you're going to have to add coefficients at the beginning of some of the species. Okay, so you want to work with the most complicated molecules first, but look at the atoms that are only going to be in the fewest number of species. Okay, so like, for example, what we looked at previously, we started with carbon because it was only in 2 of those species, one on both sides. Then we looked at the hydrogen because hydrogen was also only in 1 species on both sides. Where it got a little confusing was with the oxygen, because the oxygen was in not just carbon dioxide, but also in water. So we had to look at a few different things there. Okay, so we started with the carbon, then we went to hydrogen, and once we had those, then we could go to the oxygen. Okay. So the only other thing is, don't change the identities of any of the reactants or products. Once we know what we have, that's what's happening. Okay, you're not going to do anything by writing it differently on paper. That's not going to change what's happening in nature. So do not change the identities of what we have. Okay, carbon dioxide is not going to suddenly change into carbon monoxide just because that makes it easier on you to balance the equation. Okay, so don't try that. Okay, here's a couple of other examples that we have. And again, I would like you to do this on your own. And then in the video that I provide for you later today, I will explain how to balance these. Okay, so solid ammonium dichromate, which hopefully you know those ions at this point, or NH42, C2O7. So that's going to be our reactant, is ignited to produce solid chromium 3 oxide, which you should know how to write that out, nitrogen gas, and water vapor. Okay, so you should be able to figure that out, balance out that equation. And then for the second one, we've got ammonia gas, reacts with oxygen gas to form gaseous nitric oxide and water vapor. So again, do this on your own. Okay, this will be good practice, not just for balancing these equations, but also for writing out these formulas for these things that I am just giving you the name for. Okay, now we're going to get specifically into ions and ions that are dissolved in water, so they're in solution. So anytime that we have an ionic solid that dissolves in water, the ions are going to separate into the cations and the anions. So we're going to look at something real simple, or sodium chloride. So we're not going to continue to have the sodium chloride units. We're going to have sodium ions, and we're going to have chloride ions, or Na plus and Cl minus. So we could show that in a particular diagram, what I'm kind of alluding to here, by showing the positive and negative ions and how they would be arranged with the water molecules within the solution. Okay. So we're going to look at a specific example here. Okay, so we have potassium chromate and barium nitrate solutions. So both of these are solutions that are aqueous, meaning that the potassium and the chromate are dissolved within the water in their solution, and then the barium and the nitrate ions are dissolved in their solution. But we're going to put them together, and when that happens, we're actually going to form a yellow solid, which means that when we put those two solutions together, a precipitate has formed. So that is an indicator that a chemical reaction has occurred. But we need to figure out what that solid is. So we're going to figure out what the identity of our solid, or the thing that would not be soluble within water, is. Okay, so we're going to write out our basic equation first. So we have potassium chromate, barium nitrate balanced here, and that's going to give us products. We got to figure out what the identity of those products are. Okay, so we need to figure out what combination of ions we could get to potentially form a product. So, thing to keep in mind is, so we have a positive ion here and a negative ion here. positive, negative. What type of ions or what type of ionic solid would form out of our possibilities here? So remember, positive is not going to like positive, negative is not going to like negative. Positive is going to like negative. So will the potassium here get with barium? Is the chromate going to get with nitrate? Nope. Is the potassium going to get with nitrate? Quite possibly. Okay. Is the chromate going to get with barium? Again, quite possibly. So let's talk about what we got, right? So we are starting with potassium chromate, which in a solution we would write like this, right? We have our potassium ions, we have our chromate ions. Same thing with the barium nitrate. We have our barium ions and the nitrate ions. So when we add them together, we're going to get our products. So the question is, what is that solid? Is the solid going to be potassium chromate? Well, we already know that it wasn't in its original solution, so it's not going to be when we put them together. Will it be potassium nitrate? Well, positive and negative, that certainly fits, okay? So that's a possibility. Barium chromate, positive, negative, that is also a distinct possibility. All right, what about barium nitrate? Well, that's what we had originally in its solution, and it wasn't a precipitate then, so it's not going to be a precipitate now. So we can eliminate the potassium chromate and the barium nitrate because that's what we had originally when they were dissolved in water already. So that's not going to be our solid. So the two options that we have are going to be the potassium nitrate and the barium chromate. So I'm going to refer you at this point to your book, okay, in page 134 in table 4.1 at the bottom of that page. Check that out, become familiar with those solubility rules. That is going to be real important for you moving forward. Okay, so looking at that, you can see that potassium ions, okay, really anything that contains potassium is going to be soluble. And same thing with nitrate. Anything with nitrate is going to be soluble too. So that's why barium nitrate was soluble, and that's why potassium chromate was soluble. This contained potassium, this contained nitrate. So if we go back and we look at our options, will potassium nitrate, two things that anytime that we have an ionic solid that it's going to be soluble, is that going to become a solid? Absolutely not. All right, that is going to be one of the most soluble things you can possibly get. Okay, so that means that our yellow precipitate is this barium chromate. Okay, so again, become familiar with the concepts in table 4.1. It's going to be real important for you moving forward. Okay, so, and that is what tells us that the potassium nitrate is not going to be our possibility. So that means that the barium chromate is going to be the thing that forms a solid. Okay, so what happens to the potassium and what happens to the nitrate? Do they come together? Do they form an ionic solid? No, they stay in the solution, okay? The potassium and the nitrate, they're still super soluble. They're not going to come together and form a solid, all right, with the barium, with the chromate, with each other. So they're going to remain in there, and nothing happens to them. So that means that they are kind of just standing by, and they're going to be called what is known as a spectator ion. Okay, so looking at the complete ionic equation here. So our potassium, our chromate, our barium, our nitrate, all of our ions to begin with, okay, are all aqueous. The potassium and the nitrate, that stay aqueous, okay, we keep them like that. But the barium chromate, they went from being dissolved in the solution to no longer being dissolved because they formed a solid that was no longer soluble. Okay, so that's why we indicate it as such. So what we have here is the complete ionic equation. We have all the ions on this side, We still have all the ions that are in the solution on this side as well. Okay, but we can simplify it actually a couple ways. So we could use the complete molecular equation by just putting these together again, okay? Potassium chromate aqueous, the barium nitrate aqueous, and then putting these together, so the potassium nitrate aqueous, and then the barium chromate solid. Or we can take away the things that are common on both sides. So notice how we have potassium aqueous, nitrate aqueous on this side. And then we also have them on this side. So that means that we can just cross them out. We don't have to include them in our net ionic equation. So this is the complete ionic, okay, or you could even call it the gross ionic equation. This is our net ionic equation. We eliminated the things that were the same on both sides. Okay, so now we just have the things that changed where the chemical reaction happened. So we have the chromate, we've got the barium, okay, both aqueous, and then we have the barium chromate solid. So we do not include the potassium or the nitrate in the net ionic equation because nothing happened to them. They both remained in the solution. So they are the spectator ions. They watched as the barium and the chromate reacted together to form that yellow solid. Okay. So a little bit of information about each of these types of chemical equations. So we could have that balanced molecular equation like we did here, okay? We don't write out the ions, okay? And that certainly works. We could write out the complete ionic equation. And these are gonna be super, super useful for us to be able to envision what is actually happening in a precipitation reaction, okay? But a net ionic equation is going to eliminate the fluff and get us exactly what we want, and that is going to be the reaction that happens. So the aqueous things that have now become a solid. So we eliminate the spectator ions that are just there to watch, okay? Nothing is happening to them. Okay, so at the end of this, I'm going to give you a couple more things to practice with, and these are going to be ionic equations. So I want you to write out the complete ionic and then the net ionic equations for each of the following examples. Okay, so we have aqueous potassium chloride is added to aqueous silver nitrate. A silver chloride precipitate forms. Okay, so I even tell you what the precipitate is in this case. Okay, so write out the formula, the molecular equation, the complete ionic and the net ionic equations, and then indicate our spectator ions for this. Okay, do the same thing here for potassium hydroxide that is mixed with iron nitrate and which will form an iron hydroxide precipitate. And then for the third example, also do the same thing, show all of these types of equations plus indicate the spectator ions for sodium sulfate and lead nitrate forming lead sulfate precipitate. Okay, and when you are done with that, just hang on and wait for the second video that I provide for you later today. Okay, and then also answer the questions on AP Classroom to get credit for today.